What's going on? I just found that I failed my video interview, which is kind of untimely because uh what I'm going to be doing now, like what I was going to be doing regardless of this, is studying the very content that made me fail the interview. That's how it works, I guess. So yeah, I'm gonna start reading this book, Operating Systems in Three Easy Pieces. Uh, Primarily just to learn more about operating systems, but also because next semester I'm taking OS. And I kind of have like a lot going on next semester, so I want to make every class easy. So I'll just read this ahead of time, and it should be more of a programming exercise than anything else. Let's edit this. Semester, so I want to make every class. But yeah, so we're gonna read this book. I'll likely do the programming exercises as well, or perhaps I'll understand the homeworks and do some of the projects. I don't care to do a ton of busy work. Like I don't care to do a ton of programming exercises. But if it is generally useful, let's do it. And also, I do have this book, Linux Kernel Development. Perhaps I'll read that this break as well. But I think I have around 10 days to just do work. So I think I can get through a few books at least. Yeah, I guess I'm just gonna start getting into it. Preface, yeah. Let's do it. I'm going to new tab these. Looks good. So yeah, there are three easy pieces being virtualization, concurrency, and persistence. Appears as a security chapter as well. Also some curious appendices. I definitely read one on virtual machines at least. Each major concept is divided into a set of chapters. Make the paths of history as clear as possible. How the sausage was made. The sausage is good for. Okay. Crux of the problem. The issue that the problem is solving, I guess. We'll explain how a system works by showing its behavior over time. These timelines are at the essence of understanding. Asides and tips. Dialogue. Dialogue. Okay. An abstraction. Real code, not pseudocode. I respect that. I'm not trying to see a Pythonic implementation of virtual memory. A few homeworks and simulations. Most important addendum. KR88. Shout out to KR88. First type is systems programming concept projects. XV6. Yeah, I believe the course that I'm taking next semester is on XV6. All systems programming, all XV6 programming. Indeed, not an educator. students. Hennessy and Patterson. Respect. Acknowledgements. What the heck? Okay, I mean. Okay, cool. Okay, so that was not particularly useful, but I'll still read it. Contents. We're gonna read Introduction to Operating Systems, Virtualizing the CPU, blah, blah, blah. Excuse me. So, introduction, and we have some code as well. Introduction to Operating Systems, 20 pages. So, many millions of times. Yeah, billions. Fetches an instruction from memory, decode, execute. That's known. Von Neumann, understood. Body of software. They do many things. And Von Neumann played in the NBA for 6 years. Yeah, that's. Oh yeah, what the heck? Just clickbait, okay. Crux of the problem, how to virtualize resources. One central question we will answer in this book is quite simple. How does the operating system virtualize resources? This is the crux of our problem. Why the OS does this is not the main question, as the answer should be obvious and makes the system easier to use. How? What mechanisms and policies are implemented by the OS to attain virtualization? How does the OS do so efficiently? What hardware support is needed? We'll use the crux of the problem in shaded boxes such as this one. Yeah. Cruces. Curious. So the body of software that abstracts away hardware to allow programs to run is called the operating system, as it is in charge of making sure the system operates correctly and efficiently in an easily to use manner. The primary way the OS does this is through a general technique that we call virtualization. Sorry, and I'm kind of bad at reading, honestly. That is, the OS takes a physical resource, such as the processor, and transforms it into a virtual form of itself, sometimes referred to the operating system as a virtual machine. In order to allow users to tell the OS what to do, it has some interfaces via syscalls. You also have a standard library. Finally, because virtualization allows many programs to run, let's get a zoom here. Many programs that can currently access their own instructions and data. Many programs, it's known as a resource manager. CPU, memory, disk, or resource, the operating system manages them. It used to be called the supervisor or the master control program. Yeah, I mean, OS definitely sounds better. Let's consider this. Code that loops and prints. So it'd be kind of nice just to get a cd temp, megdir, os tap, cdos tap, and just clear here, and just get a little dir for doing stuff, writing some C, yeah? So, just in the habits of writing programs, just trying to actually do all the exercises here. Let's try to write some of this. Standard IO. You want syslib. Start standard lib. Get a time in there. Time.h. Perhaps sys/time.h. Once assert.h. Assert. Is that a thing? Assert. Perhaps it's assert in a different context than what I'm imagining. Include common.h. So local header. Does that mean that, yeah, we have common.h. Spin. So, I mean, there's common.h. Common threads.h. Get time and spin. It can be too much of an inconvenience just to make this, yeah, so let's make an includer such common.h. I should just copy this, yeah. Should unclear identify null. Just think. C standard def. So what are ODR? What is an ODR violation? One definition rule. I don't necessarily think that's problematic. I mean, okay, I got to tend my plant. How long? That is a, oh, that's a permanent measure, okay. So let's just act like we know that exists. This is going to be include slash, yeah. So what are we doing here? Int main, int argc, argpointer arg v, array. So if arg count is not equal to 2, printf standard error, print what? Usage CPU string slash n. So is it a format string, and that's why, yeah, so we're just ignoring the format. Exit code 1. So otherwise we're doing this car pointer stir. So just copying the arg1. Sorry, now we're just getting a pointer to it. While 1. Spin 1 tick. I believe that parameter is like, and we're just print effing %s slash n stir 0. Right, so seems good enough. GCC-L CPU. So okay. So I think that is implying this is called CPU.c. CPU.c dash warn all. C standard def. Use of undeclared identifier null. Is this because I'm on C? Some other version of C? Huh. Pointer does it want? Looks like it wants no pointer. Okay, it thinks I'm writing C++ in this header. No pointer T. Dude, it thinks I'm writing C++ in here. Yeah, it thinks I'm writing C++. How do I tell it I'm not writing C++? OSP thinks my C header is CPP. Whenever I write C++, I just use HPP. So that H. So let's look at Mason. This is a bit AIDS. Guess we can update these packages. Go please. Nothing on Go please. Spawn Go 5. Requires Go. So it looks like I wanted a better Go version. We might go on here, so 2 dissatisfied. We'll just ignore the OSP. Honestly, OSP stop. In true like C programmer fashion, perhaps I just won't use the OSP at all. So let's run ./CPU. The character, the string A. So every tick of that thing, spin for, let's go to the definition of spin. No OSP client attached. Boolean. So spin, how long, we get the time, minus t, so less than double how long. So we just wait until our time elapsed is equal to our time provided. Looks like a second. It's kind of interesting. Do dot slash CPU A and dot slash CPU B and dot slash CPU C and dot slash CPU D B A Alright, it doesn't look like that too much. Does it need the end at the end? A. It looks like it doesn't want mine to run in parallel. Because this is making 4 processes. Mine doesn't appear to do that. I mean, I understand the concept. RIP. One processor. Virtualizing the CPU. Talk about these APIs. Should run. That's the point of scheduling. So I think most of what this book is on, I mean, looking at introduction to paging. I mean, just looking at the chapters, most of this, perhaps half of this, looks like it was covered in this book I read earlier. This one, memory mapped IO, all of this. So definitely introduction to paging, perhaps concurrency bugs, concurrency in threads, thread API. Maybe not as much as the code portion of the thread API. I mean, if you're talking about like pthread and such, I mean, certainly, but IO devices. So I should be able to get through this kind of quickly. I'm trying to go back here, yeah. Or no, I'm just going here. So we have many policies. Answer the questions. We learn about the basic mechanisms that the operating systems implement. One of the OS is a resource manager. Doing so runs some job in the background in the ZHS. Yeah, I'm using ZSH as well, yeah. Program that accesses memory. So yeah, let's run this. As an exercise, we can do distributed binary and do, sorry, this was mem.c. So let's include unisted. I've never seen that header. Unisted.h. POSIX. This is like fork exec. Maybe I have used this. It was just in a header that was abstracted from me. So we're gonna include standard IO. Didn't really read it, but I imagine the next one is standard lib.h. We're gonna include common as well. Include / common.h. So we have an in main. We are malloking in it, asserting that it's non-null. So I guess this is the assert thing. I haven't seen that. Let's see. Int main int argc arg wait, what am I doing? Argv unwashed array pointer argv malloc ap assert. It's from cassert. Interesting. Assert that p not null. Can printf the address. Printf is %d, so the decimal address pointed to by p. So it wants to print the pointer as well. what is it doing? Colon here? Yeah. %p/n \n, sorry. Now we'll come in here and do p. We'll dereference p into p, yeah. No, I'm dumb. This is get PID. Get PID. Huh. Didn't think that'd be the address. Oh no, this is literally the process ID. Okay. This is the process ID, and then it's going to say address pointed to by P is the address. Oh, okay. That makes sense. Start P equals 0. Start making the int actually 0. While 1. Spin 1. Increment P. Printf. We're going to do the same process ID here. P, or print P, %P. Looks like I wanted a /n. And I want to get PID and P. And 0. So let's just try GCC -o. I don't really care about naming the object file, honestly. Just make it mem.c -wall. That slash, it's gonna be like a A1, yeah. A.out. Just pointed to by this. That's the process ID. See address pointed out. Sorry, this wanted the value up here, not the address. Nice LSPR, that helped me. 1, 2, 3, yeah, okay. So I'm really surprised this is running in parallel. I didn't think that's how that worked. Mem and oh yeah, ./a and ./a. Huh? A.out and A.out and okay, so now they're going in parallel. Impressive. Certainly not the same address. I wouldn't think that printing the address would print the virtual address. I thought it would actually point the physical address, yeah. Maybe this is just an example. Address space randomization disabled. Ah, okay. So I guess it is still the virtual address, but it's just with address randomization. Noted. I would actually like to read on that. We'll see. So that's virtualization. Concurrency. So we're already getting into this. Well, that's kind of cool. So they're gonna call this file what? Intro. This is gonna be threads.c. Excuse me. Wait, how do you start the process? Wait, how do you start the process actually? Okay, it's kind of humorous. Let's see. So this one's called threads.c. So we're gonna want the common threads.h. Semaphore. Wait. Samoid. Thank you, dude. If I knew this like 2 days ago. I feel like I kind of don't like these abstractions. It's my initial reaction to them. Just for like learning this, but let's see. That's not what I'm trying to do. I'm trying to get here. So let's include standard IO, include standard lib, let's include common, similarly common threads, volatile and counter 0. Initialize it into oops. So let's go ahead and look C volatile keyword. Don't really recall what this does. Prevent the compiler from applying optimizations. That can be changed by scope outside the current code. Always reads it from memory instead of keeping it in a temporary string. So the utility global variables modified by an interrupt service. Yeah. Modified by a multi-thread application, just any other parallel way, I guess. A lot. So the worker, which goes through the amount of loops and increments the counter, returns null. So let's write this. It's actually a function. That's returning a null pointer. Okay. Worker. What is the input to this? Void arg. I'm unsure of the utility of void arg, but I guess say so we're doing int I. What's the point of doing that instead of just doing for if I goes 0, I is less than loops, I plus plus, counter plus plus, and null. And then we have int main, int argc, car argv. So if argc neck 2 printf usage, how do you use this? Or what's the printf standard? F printf standard error. It's a stream. I don't think we're having any formatting here. We're just doing usage threads value. So remember. And we're exiting with a code of 1. Okay. Otherwise, so okay, the amount of loops it wants is equal to argv. So this is going to be an int array cast, yeah. Sorry, int pointer cast. Never mind, it's already up there. Int argv1. So we're going to do pthread, pthread t, p1. It's kind of acting like that didn't exist. p1, p2. Printf. Initial value %d / n. We want loops, yeah. Sorry, counter. Initial value of the counter. So we're doing pthread create thread p1 attribute null. Okay. Between worker arg null. Looks like you just need an arg. Oh, wants an A2 on it. And then we're joining them. So Peter join does not take the notes. Yeah. Dash pthread. It's like linking the library or some junk. Oh, this is, yeah, that's the amount of loops. The amount of like 100,000. So yeah, I was a bit confused by that. The shared counter is incremented, takes 3 instructions. They don't execute atomically. So that's just a Just talking about bad persistence. DRAM store values in volatile manner. Power goes away, it's gone. Need hardware, software to store persistent data. IO, hard drives, SSDs, file system. Shout out Emacs. Create and edit a C file. Use a compiler. Run the executable. Share the file across different processes. Store? If you're using Vi, there's probably something wrong with you. Emacs, dude? Come on. Bro is 80. Bro is 80 at youngest for sure. Minimum age 80. Forgot about this thing. Window capture. This one, yeah. Not this one, yeah. Yeah. That's cool. Alright. Berlin. Here. Program that does I/O. This one is opening a file. O Ron Lee O create O trunk S. So I'm not gonna write too much on that. I'm not gonna copy the code on this. Hello world into a file. You call open. Call write. Call close. System calls are routed to part of the operating system called the file system. What OS does in order to actually write to disk. We would show you that. We would show you, but you'd have to promise to close your eyes first. That is unpleasant. Yeah, file system does fair work. Where will the data reside? Keep tracking it in various structures. The file system maintains doing so requires issuing IO requests. Device driver knows getting a device to do something on your behalf is quite difficult. Requires a deep knowledge of the low-level device interface and exact semantics. Portion of the OS provides. Do it through the extended lib. Of course, there are many more details on how devices are accessed and how file systems manage the data persistently across atop said devices. For most reasons, most file systems first away writes, buffering them. Most file systems writing protocols such as journaling, copy and write. So, crux of the problem, how to store data persistently. File system is part of the OS. You're managing persistent data. What techniques need to do it correctly? What mechanisms? How is this achieved? To make different common operations efficient, file systems implementing different data structures. RAIDs, design goals. So now you have some idea of what an OS does. Physical resource CPU virtualizes them, does concurrency, makes them persistent. So we have trade-offs. Most important basic goals is to build some abstractions in order to make the system easy to use. Fundamental to everything we do. Have language like C without thinking about assembly. Assembly without thinking about logic gates. Gates without thinking about transistors. Forget about its importance, but we won't hear it. I'm going designing and implementing an operating system is to provide high performance. Minimize the overheads of the OS. Virtualization and making the system easy to use are well worth it, but not at any cost. We must strive to Some of you might object to calling C a have language. Remember, this is an OS course, though. That's what we have having the code. Assembly all the time. Real. Must provide virtualization of their OS features without excessive overheads. These overheads arise in a number of forms: extra time, extra space. Minimize both where possible. Perfection is not attainable. You provide protection between applications, as well as between the OS and applications, so separating the kernel space and the user space. Begin programs run at the same time. A distinct process, memory spaces. Protection is at the heart. Isolating processes from one another. Run non-stop, that fails, all applications will fail, so it must be highly reliable. Energy efficiency is important on occasion. Not in my case. Security. Yeah, mobility. I'm not too worried about that. But yeah, there's different trade-offs. That's what this has. Some history. Skim this. They were at one point just libraries. Batch processing. And system calls. Multi-programming. PCs. Unix. Yeah, BSD. I don't really care too much about the history, honestly. Next step. Yeah, okay, whatever. Summary. Graphic. Yeah, okay, sure. References, sure. So that's the introduction. Okay, 1 out of 6. Part 1, visualization dialogue. Is this like actually... What the heck? Okay. Whatever. Processes. So I think I understand processes. So quick doing a page check here. That was 13. You have 24. You have 51 of these. 1351, about 600 pages. So each one of these. Yeah, okay. Each one of these is like 1.5%. I mean, I guess you could have just looked at that from this number. So I'll probably read. How long have I been streaming? It's been an hour already. Has it actually been an hour of me reading this? That's kind of crazy. So let's read what the process is. So we're creating the illusion of many CPUs using concurrency. Virtualizing the CPU. Time sharing the CPU. Mechanisms. Time sharing. Space sharing. Context switch. Policies are algorithms for making some kind of decision within the OS. Yeah. Scheduling policy. Process. So yeah, I understand this. We have a process. We're running program. Constitutes process. Machine state. A program can read or update what is running at any given time, what parts of the machine are important to execute. I'm going to read this chapter and then work on request. Memory. Instructions lie in memory. You give an address space to the process. You also have the general purpose registers. You also have the program counter and the stack pointer and the frame pointer. Common design paradigms to separate high-level policies. Modularity, yeah. Okay, so the process API, that's what I didn't really get to in my previous courses much. Process, like the actual Linux APIs, or perhaps Unix POSIX APIs. Okay, never mind. Create, you have to create a process. You must destroy a process. You kind of want to wait on a process. Sometimes you want to suspend a process and resume a process. You also want to get the status of a process. So let's consider from program to process. You have your static program data on the disk and you load those pages into memory in a process's address space, I would call that. Yeah. A little more detail. One mystery that we must unmask a bit is how I love unmasking a bit, dude. That's kind of good. Is how programs are transported into processors. Specifically, how does the OS get a program up and running? First thing the OS must do is load its code and static data into memory from disk as an executable. Loading process is occasionally done eagerly. You load everything. Or sorry, that was in original operating systems. Now everything is lazy. Loading pieces of code or data as only as they're needed. Paging and swapping. That's already understood. Understood. Stood. Once the code and static data are loaded into memory, there are a few other things the OS must do. You must allocate memory for the runtime stack or just stack. C programs uses the stack for local variables, parameters, return addresses. The OS allocates this memory and gives it to the process. The OS will also likely initialize the stack with some arguments, like the main function, the argc, and the argv array. OS may also allocate some memory for the program's heap. In C programs, the heap is used for explicitly requested dynamically allocated data. Programs request set space by calling malloc, and free it explicitly by calling free. Heap is needed for data structures such as linked lists, hash tables, trees, and other interesting data structures. The heap will be small at first as the program runs, and requests more memory via the malloc library API. The OS may get involved and allocate more memory to the process to help satisfy such calls. The OS will also do some other initialization tasks, particularly as related to input-output. So each process has by default 3 open file descriptors: standard in, standard out, standard error. You can run from the terminal and print output to the screen. Learn more about I/O, file descriptors, and the like in the third part of the book on persistence. States. So we know what a process is. Let's talk about the states it can be at any given time. Simplified view, you can be running. You can be ready. Or you can be blocked. In a block state, you have to perform some kind of operation, such as I/O from disk. And ready is like it's unscheduled. Okay, it's in the ready queue. Makes sense. If we were to map these states to a graph, yeah, so ready to running means it's scheduled. Running to ready means it's been descheduled, blocked, and has to do with that. So that's understood. So you have a scheduler that does all this, sure. Data structures. So you have a process list, a process control box. Some kind of process list for all processes that are ready and some additional information to track which process is currently running. OS must also track blocked processes when an I/O event completes, all this other stuff. So figure 4.5 shows this. What we need to track in the XV6 kernel. Similar process structures exist in real. Yeah, the Linux one is super complex. I mean, you can't even tell how complex it is because of all the macros. From the figure, you can see a couple important pieces of information: register context. So XV6, you have these registers, I guess. Different processes, states process can be unused, embryo, sleeping, runnable, running, zombie. Information XV6 tracks, including its register context and state. So you have mem, start process memory, size of process memory, bottom of the kernel stack for this process. So I don't know what a kernel stack is for a process, but we'll see that. Process state, process ID, parent process, if 0, sleeping on Chan. If non-zero, if non-zero, you're sleeping on this channel. If 0, the process is killed. You have a list of open files. You have a current directory, which is a inode. So curious what the inode type is. You have a context, switch here to run process. You have a trap frame for the current. So switching between them implies a context switch. There are a lot more states. Initial state, you have final state. It's called the zombie state. Systems are replete with various important data structures. Process Swiss is the first data structure. Simple ones from the NEOS that has the ability to run multiple programs at once, but something akin to the structure in order to keep track of other running programs in the system. Sometimes people refer to this as PCB. Fancy way of talking about a C structure that contains all the information about a process descriptor. So we are already at the summary, interesting. So yeah, you have the wait syscall, wait for the completion of the job, indicate to the OS to clean out the relevant data structure. We've summarized the most basic abstraction of the OS process. Before we get into the nitty-gritty, side process key terms, process, stack pointer. Yeah, so I understand that. That's already been learned. Homework, simulation. So I think I'm good. Personally, I think I'm good. So that's process. Now we're going to talk about the process API. But before we do that, I'm not even going to change the title because I'm just going to start working on request. Bit tired. So let's look at my profile. Let's go to request. So I believe I have a PR. I have some like local junk going on right now. Q out of this. Oh, let's go here. Q. CD into request, yeah. Clear summon parser format. It's lazy, get it? So parser format. Comment. So what's the difference in this and master? Git log. I should just look up. Main is at this, so implement parser errors, C to dos. Insertion is a vec, remove comment and format. So let's just go into here. I'm not sure of the state of this. We can see into build, cmake dot. Can cmake dash build dot. Make that the build there, and then here we can go data slash site data slash source slash request data slash examples slash. Let's do post dot rack. Get that. Let's do data slash examples slash errors slash JSON missing key dot rack. Let's do the PE from section header. So that one looks good. So I want to get these assertion errors looking nicer and some other stuff, but first I'm going to the back. Probably stop drinking energy drinks. Cause damn. Alright. Scheiße. So let's go back to this. What I'm trying to do. Let's go to the GitHub project, yeah? So there's a PR. Resolve 22. So yeah, I'd rather just stack this. Something else. I need to pretty print assertions. I need to pretty print the actual content. I need to print like compiling whenever we're doing something. Stack. So how do I want to do this? Let's get parser error, malform section header info. So let's go more into this. And so where are we actually creating this? Yeah, where are we throwing this? Here. So we say missing. So it looks like we don't do this. Const info. Missing closing bracket. So parser error. So in main, I want to print the error head and print the error foot, which implies having some kind of application context. Which is kind of why we need this concurrency model. You know what I'm saying? Problem is that the libcurl, it's hard to do with libcurl. Error.print. So currently error.print does this. So print details. So it does the old malform section header, does the line, the file name, does this in bar. So what if I do like 2 malform section headers? I do like request is malformed and headers is malformed. Just stops after the first one. So it stops after the first one. Okay. So I guess in the print details implementation, so it's going to be a lot of implementations of these, and it's going to switch based on. So it's not even print details right now, is it? I'm going to print the file, there's specific details in bar. So it's got to be someplace where I'm printing this. Const 0. So I guess it's not sharing the override in here. Sorry, in the here. Print details. It's a visitor. Looking at the actual thing within the visitor and printing it like this. So here we are leading with the deadline. Printing. So let's go back to air. Cargo build. It like shifts it over as much as it needs to make the error. So in the case of malform section header info, deadline. And you're going to print a line in left pad. Terminal line number. Then you're going to print the arg.snippet. Then under that, we're print the hint. So you're going to print line and left pad standard. So let's do here. Print the hint. Standard not. And we're going to print, let's just imagine we printed hint add closing bracket. So this has no format. Hint. So what we need to do is we need to save a thing. We can do hint. So hint can be cyan. Yeah, the light cyan. So determine a color bright cyan. Add closing bracket. Right. Now we need to do is get the length of this and offset all the lines above it before by this. Lead with a deadline. Right line and left pad. So we're going to print line and left pad. Okay. Lead with deadline, in with deadline. Then we're going to print the hint. So print line and left pad, line number. Center no, so this is going to be snippet. So here we'll have a to do pad snippet by len of hint. So we'll have here comp time hint text. So we can have a standard string hint text is equal to add closing bracket top. Comp time. Is that a C++ thing? C++ comp time. Const expr. I think I'd already know that's comp time. Hint len. So here we'll do an int. Sorry, we'll do a standard string get string get white space. int spaces. That's what this is doing. So what you do, int digits, so you do this, yeah. If line number has value. So let me just do this. Line number of spaces. Spaces. Wait, no. How do you just print standard string? Yeah, so it's just this actually. So we can put this. Spaces. And as we can do as white space. Sure, like as white space. That makes sense. So here we'll do as a white space int text.length snippet. So in theory it should be padded, yeah. So it is. Now you have to factor in at the index that I'm trying to get at. How would this do it? So then you gotta offset it by the index of the line. So you want to get as white space, but minus the length of the snippet. The snippet. So arg snippet. But then you're gonna do +1. Could actually be -1, but it's easier to just click it and test later than actually no. It's -1. Huh? And save it. So now the only problem is I want to have a hint tag. So I'd like to have this bold tag, bold text. So where we're doing the hint, I like this to have a thing that's determined called by Cayenne. This, or with format emphasis bold, yeah. Blend bold. And I'd like to have just some text here that says hint. And so we're going to count in the text that says hint here. So it's going to be 4 plus that. It's actually going to be 6 plus this. Hint. Add closing bracket. So that's pretty good. It's a good start. Next up, I think this error here. So wherever in the original, so let's delete this, let's open this. Go to the print function, just the error dot print. Definition of this. End bar, this should just be a new line. So it's format dot print. Literally, it's a new line. End with new line to separate errors. So this should look okay. Int parser. So then we print the bug. So then back in main, I'm doing format print. So we're kind of doing what we did here. So we should actually just call, we should have an error context here. So this is where we get into having an application context. But I think that looks good for now. So how long have I been streaming? Hour 30. Okay, I'm gonna pause here, run to the Amazon locker, and I'll be back. So I'm gonna end the stream. I'll come back for another stream. We'll read some more operating systems. Excuse me, and we'll work on some more requests. But yeah, I'll see you.